Rosen also looks different than what I thought.
What did you think she looked like?
She looked different, but also just as good as I thought she looked. I thought she looked decent and put together. And
You don't think she looks decent?
no, I said she does. She still does look decent and put together, but
Oh.
the physical appearance is a little different than what I thought. I imagined her a little bit thinner and perky. She looks a little perky, but not as thin. Swimming team.
Oh.
Hi.
Where am I seeing that? Bad deal.
God. Bad BO.
You following me, Jen?
Wow. Okay, I guess I'll get started. I don't know how many people are really watching. It says that there's like 7, 8 people watching. Uh, so I don't know if anyone got the updated link, but I this is my first time doing this, and I don't know really if it's gonna be a success because I'm seeing some of the video playback and it's kind of low quality, and it's probably because I'm uh downloading a lot of stuff. So sorry about that. Okay, so I kind of want to do some short answer questions from the June 2013 Regents. I was looking over those short answer questions, and those are, I think, a good mixture of some stuff that you may see tomorrow. Um, so I don't know if you guys have your green books or access to the June 2013 Regents, but I'll post. Who is that misguided ghost? Okay. Anyway, it's weird to hear my voice like 30 to 40 seconds later after I say something. So anyway, I put the link to the June 2013 Regents in the description, so you can click on that. I will go over some questions you guys have, but I want to go over each one of these short answer questions just to make sure that we're clear about how to answer each one of those, and then I'll answer some of your questions. So if you guys have any questions, just like put them in this like comment thing that's on the side of the video or whatever. So let's see. Let's see how I can do this. Okay, sorry. All right, so question 51. Wow. Question 51, 52. It's I'll try to go as fast as I can, Alexis. So it says a 25-meter length of platinum wire with a cross-sectional area of 3.5 times 10 to the negative 6 meters squared, has a resistance of that many ohms at 20 degrees Celsius. Calculate the resistivity of the wire. Show all work, blah, blah, blah. So let's see if I can make this bigger. Whoops, I can't. Sorry about that. So we have this, which is the length of the wire, which is 25 meters. This is a resistivity question. It's asking for this value right here. And there's just one equation on the reference table that asks about resistivity. So we need our length. It gives us cross-sectional area here. A equals 3.50 times 10 to the negative 6 meters squared. And it says that it has a resistance R of 0.757 ohms. And the temperature is 20 degrees Celsius. We don't need to add that because we have to assume that it's at room temperature, and 20 degrees Celsius is at room temperature. So it's asking for resistivity. Resistivity is given by this funky looking P symbol. It's rho. Okay, and this is what we're solving for. So this is all step one of listing out our variables, right? Our next step is to pick an equation. Well, in the reference table, I think it's page 3 under electricity, we'll see resistivity only appears in one equation, and that equation is R equals resistivity times length divided by area. So we plug in our values into this formula. So R is 0.757. Rho is what we're solving for. L is 25. And A is 3.5 times 10 to the negative 6. So notice I didn't put in my units here because I already have my units listed here. My units are already here. So I don't need to plug them into the equation again. Okay, so I have to solve for this. I don't really have a calculator on hand, so I'd probably fail the Regents if I did that. So I don't know really what the answer is. So rho equals, let's cheat a little bit. So the answer is rho equals 1.06 times 10 to the negative 7. And the units are ohm meters. Okay. This is what the answer is. I can figure out what my units are by either plugging in my units and then doing some dimensional analysis, or I can go onto that page of the reference table that shows resistivities, and it tells me that the units are ohm meters. Okay, that says that on the reference table. So that's something. Okay, and Rahat, I'm just seeing that it says, I don't know if you can, yeah, I can't fix any chats. I think you guys have to like log in to a Google or your Yahoo, not your Yahoo, whoops, YouTube account. If you ever use a Yahoo account, you need to upgrade. Sorry about that. So, yeah, I'll go over incline in a second, Bajinder, unless you have somewhere to be. Okay, so I'm gonna move on. You guys, I guess, can just like rewind the video and like look at the process, I suppose. That's something you can do. So the next question, if we're going through this, I'm gonna skip number 53. No, I'm not gonna skip number 53. Let me not skip anything. This was a question that I gave on that alternative final for some of the people that decided to be stupid and take the alternative final to lower their grade. I'm gonna do this question. So this question Oh, thanks for that calculator. So this is this question, number 53. The diagram below represents a periodic wave moving along a rope. And the question asks, on the grid in your answer booklet, draw at least one full wave. Sorry, let me put the question up too. No offense, Alexis. Did you get my final? Who is Misguided Ghost? I'm so sorry. Who is that? Not NY Dollars? I hope that's not Naya. Gross. Okay, I'll talk about projectile motion in a second. All right. We need to go over these waves. I'm not sure if you guys if everybody that's watching knows how to do this type of stuff. So I'm going to change my color. Sorry. Anyway, so the question says, on the grid in your answer booklet, draw at least one full wave with the same amplitude and half the wavelength of the given wave. Hi. It's a car. So half, this is about one, and I don't know how many waves this is. This is one and some wave. This is more than a wave. So we're going to take from here to here, and we have to shrink it half of the wavelength of this given wave. So how I'm going to do that is I'm going to see that the wavelength from 0 to 4 is where my one wave is. Okay, so half of that would be here at 2. So that means I need to draw my wave like this. Well, you guys would probably draw a little bit better than that. That looks like crap. Okay, anyway, so this is what the wave looks like. That's what the same amplitude wave, but half of the wavelength given looks like. You guys hopefully are better artists than I am, so you'll do that. Yeah, Misguided Ghost, thanks. It's 1 1/4 wave. Thanks. Okay. Anyway, so wow. I don't know if you guys are seeing the video very, very blurry, but to me it looks kind of blurry. My bad. Okay, so I apologize for that wave. Anyway, that's what it should look like. It should only be it should only go up to this 2-meter mark as the position. Okay, so it's literally half of that. I want to go on to the next 2 questions because the next 2 questions have to deal with impulse, and we didn't spend a lot of time on impulse in class. So this question, it says something like a baseball bat exerts an average force of 600 newtons east on a ball, imparting an impulse of 3.6 newton seconds east to the ball. Calculate the total amount of time the baseball bat is in contact with the ball. Show all work, blah, blah, blah. So a baseball bat exerts an average force of 600 newtons east. So we're going to do F equals 600 newtons, and then we can say like east. Okay, now this average force, this is another name for the net force. So we can say F net equals that. Okay, now this bat imparts an impulse. Impulse is given by J, impulse of 3.6 Newton seconds east on the ball. calculate the amount of time the baseball bat is in contact with the ball. This is a very simple one. So it's asking for time. The question, the equation that we have to use is on the reference table. It's an equation that looks like this. J equals delta P, and it also equals F net times time. So we're not given change in momentum, but we're given J, impulse, and we have one of these variables, F net. So we're going to use, the equation we're going to use is J equals F net times T. So J is 3.6 Newton seconds. F net is 600 Newtons, and we have to multiply by time. We have to solve for time. So we're going to divide both sides by 600. And let's see what I get. 3.6 divided by 600 equals, what the heck? Equals T equals 0.006 seconds. That's okay, or you can say that it is 1, 2, 3, 6 times 10 to the negative 3 seconds. 1, 2, 3. Yeah. So either one of these answers is correct. Okay. Change the quality under little settings button. Put it to 720. Okay. Anyway, okay, so that's that question. This one is a very easy question. It's very straightforward. The next question is a magnetic field one. That one's really easy too. I'll go over it just for completion's sake. I may actually be saying all of them are easy, but that may not always be true, because I'm like the physics teacher, so of course I'll think everything's easy. Okay, so number 56, it says the diagram below shows the north pole of one bar magnet located near the south pole of another bar magnet. On the diagram in your answer booklet, draw 3 magnetic field lines in the region between the magnets. This is very important. They say 3 magnetic field lines. If you do more than 3, you risk getting the entire question wrong, because how the physics regions will be graded is if you, let's say, draw 5 magnetic field lines, those additional 2 magnetic field lines have to be correct. So you could draw 3 correct and then 2 could be wrong, and then you get the whole thing wrong. So don't overdo it. I know some of you guys like to drag stuff, so just do 3 if the question asks for 3. So in the diagram below, draw 3 magnetic field lines from the region. So this is going from north to south. I know that my lines go out of the north and into the south, out of the north into the south, out of the north and into the south. So this is sufficient. You do not need to draw more than that. Okay, 3 is fine. My arrows may be a little bit anyway, let's move on to the next question. Okay, the next one, 57 to 59. Mr. French, can you go over the right-hand rule? Right-hand rule. Please, right-hand rule. Okay, let's go over some right-hand rules. There's really only one right-hand rule. I know I taught you guys 3, but there's really only one right-hand rule that you guys will have to know for the regions. It's if you have some type of wire, okay, this is a side view of a wire, and what's happening is we have some type of current going through the wire, okay? Let's say current is being pumped through the wire this way, okay? There's electrons going through this wire, and the current is moving in this direction. Okay? So what you have to do, it's going to be difficult to use the right-hand rule on a virtual screen because I can't put my hand there, but the current is your thumb. So you point your right hand thumb in the direction of the current, in the direction of the current. Then what happens is you let your fingers like relax. You let the rest of your four fingers, your pinky, your ring, middle, and index finger relax. And you just let them like curl around the object. So when you let your fingers curl around your object, that's the direction of the magnetic field that becomes induced. Okay, so your thumb is your current, and your curl of your fingers is the direction of the magnetic field. And what we actually see is at the top here, right? At the top here of the wire, your fingers are going what I've taught you guys into the page. Into the page are given these X's. These are actually crosses. So into the page means crossing into the page. And if you were to rotate your hand with your thumb still pointing in the direction of the current, your fingers will continue to curl and move and go into the page and then come back around and come out of the page at the bottom, given O. O is out, X is cross. So cross into, and 0 or O's out of the page. Okay? That's about it. You're probably just going to get a question saying something like, what is the direction of the magnetic field at the top of this wire? Or something like, here's point P. What is the direction of the magnetic field at point P? Well, the direction of the magnetic field at point P is into the page. Into the page. Whoops. Page. Okay. So inwards means into the page. Misguided ghost. All right. So into the page is at the top, and at the bottom it's out of the page. So at the top of the wire it's into the page, at the bottom of the wire it's out of the page. If we were to flip the direction of the current, let's say that how do I erase? That's really stupid. If I were to flip the direction of the page, sorry, the direction of the current, what would happen is that okay, I don't know what the hell I'm doing. If I were to flip the direction of the current, if my current were to go this way, the wire the in and out would be switched as well, right? Because now I'm flipping my hand where my palm is facing me. Okay, so if the current is going to the right, my palm is facing me. And so at the top, it would be out of the page. And at the bottom, it would be into the page. Okay, so as I curl my fingers, the magnetic field is at the top coming out of the page and at the bottom going into the page. Okay. Okay, so that's the right-hand rule that I think is gonna happen, that could happen on the Regents, but they didn't have any magnetic field questions last year, and I don't think there was one in 2013, but I think there was a magnetic field question in 2012, and it was just basically asking what causes a magnetic field, and the answer to what causes a magnetic field is moving charged particles. Okay, so let me write that down. Moving charged particles. create magnetic fields. Why am I writing so slanted? Anyway, moving charged particles create magnetic fields. Basically, electrons that spin. So spinning electrons generate magnetic fields. Okay, electrons also create electric fields. So a stationary electron creates an electric field, but a moving electron creates spinning fields. Okay, I'm gonna do some projectile motion and inclined planes since you guys are just bitching about that. So I'll do that. Let's see if there's any questions that I can steal from the short answer question. Nope. Nope. Girl ride her bicycle. I don't care about that girl. That's nothing. Okay. Give me a second. Let me find a question, and then I'll do some projectile motion questions, okay? Okay, so just give me like 2 minutes to find a difficult projectile motion question, and then I'll do it. Okay, I found this question. I took away the short answer, the multiple choice. So we'll just kind of have to figure this out. So it says two spheres, A and B, are simultaneously projected horizontally from the top of a tower. Sphere A has a horizontal speed of 40 meters per second, and sphere B has a horizontal speed of 20 meters per second. Which statement best describes the time required for the sphere to reach the ground and the horizontal distance they travel? Okay, so this is actually easier than I thought. So if we want to draw a picture, let's say this is the tower here, okay? That's my tower. It's a wizard's tower. Here's my chimney. So we're going to have two spheres. Let's say this is sphere A, and let's say this is sphere B over here. So sphere A has a horizontal speed of 40 meters per second, and sphere B has 20 meters per second. Okay, and what's going to happen is gravity is going to pull these things down. So these these balls will be, these spheres will be thrown horizontally at different speeds, and they're going to land at different distances as well. Okay, they're launched from the same height, so that means that the time is the same for both of them. Okay, the time for sphere A equals the time for sphere B. They equal the same because they're launched at the same height, so the time has to be the same. Doesn't matter about the speed. They'll hit the ground at the same time because remember, everything falls at the same rate of acceleration, 9.81 meters per second squared. So that means if two things are dropped or thrown or fall from the same height, they'll hit the ground at the same time. There's actually a Mythbusters episode about a bullet being dropped and a bullet being fired, and the bullet actually hits the ground at the same time. The one that travels like 100 meters and the one that falls like 1 meter, they hit the ground at the same time because they're at the same height. Okay, so anyway, the thing that is different is the horizontal distance they travel. So sphere B will have a path like this, 20 meters per second. It's kind of fast, but it's not as fast as 40 meters per second. 40 meters per second will allow it to travel much further. Okay, actually double the distance. It'll travel double the distance because the speed is doubled. And we know it's doubled because of the equation V equals D over T. So if we double the speed, meaning if we put a 2 in front of V, time stays the same. So that means we have to put a 2 in front of the distance. The distance doubles, a horizontal distance. These are x components. Okay, so the distance is doubled. This is D, and this is 2D. 2 times the distance. Okay. All right. Do you guys want to do another projectile motion question, or do you want me to move on to inclines, and then I'll do absolute index of refraction? I'll wait. Can you find anything if they only gave you horizontal speed and vertical speed of the same object? Yes, Abdullah, yes you can. There was a table that I did for you guys during that Regents prep that one time where I was like, here, I'll just draw the table, where we had X components and Y components, and we did V initial, V final, distance, acceleration, and time. So if this is our projectile motion table, okay. Acceleration in the X direction is always 0. Acceleration in the Y direction is always negative 9.81 meters per second. Distance in the X direction is always given by the equation Vx times time. Distance in the Y direction is given by that complicated one on the reference table. So if they only gave you the X component, if they only give you the X and the Y component, you can figure out everything else, right? Depending on the situation, because if the problem was a problem where it was launched from the ground, meaning that you had like something on the ground here and it's launched at the ground, you know that the vertical speed at the height, right? This vertical speed equals 0. Okay, so you could use this as your final speed or your initial speed, depending on what you're given or not given. So you can be given only one thing, and you can fill in all the rest of these blanks. Okay, but these are always a given. A is 0 in the X direction. D in the x direction is Vx times t, and A in the y direction is negative 9.81. Okay, so let's do another projectile motion question. Let's see if I can get a really, 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 really hard one. Calculate the magnitude. Oh, describe how both no, I don't want to do that one. No, I don't want to do that one either. That one's really annoying. Don't want to do that. Don't want to do that. Okay. Okay, so I'll do this. I'll do this one. Okay, I'm gonna post what the question is. So so this question says a projectile is launched horizontally at a speed of 30 meters per second from a platform located a vertical distance h above the ground. I think we did this before. The projectile strikes the ground after times t at a horizontal distance from the base of the platform. I think the question says calculate the horizontal distance if t equals 2.5. So the question's asking for find dx if t equals 2.5 seconds. This is what the question is. This question was from 2005, June 2005 Regents. All right. So we're only given one thing here. We're given horizontal speed, right? This is what you were saying, Abdullah. Could you find something if you're only given one thing? And this is that vertical. I mean, this is that horizontal speed. So we have Vx equals 30 meters per second, and they give you time. T equals 2.5 seconds. And I said in the previous question, if we want to find dx, then the only thing we use is this one right here. This is the only equation we can use to find dx. So dx equals Vx times t, which is 30 meters per second times 2.5 seconds, which equals 70 meters, something like that, I believe. Or 75. Whoops, it's 75. You're right, Bajinder. My bad. 75. Stamp. Just kidding. Stamps are expired. So the other question they'll ask is like to draw the motion, the trajectory. The trajectory is literally just a parabola. So you just draw a parabola. Projectile motions aren't that difficult. It seems like it's overwhelming because you have all these different components, X and Y. Just remember the rule. I wrote it down in that Regents prep guide that I gave you guys. You cannot mix X and Y components in the same equation. So if you're solving for a horizontal component like distance, horizontal distance, you cannot use any vertical variables. All right. So I want to move on to incline planes. Okay. Let's see if I can get one here. Motion in a plane. No. Mechanics. Dynamics. Friction. Frictional force. Oh God. Let me find this stuff. Projectile motion. Kinematics. Okay, I guess I'll have to use this one. Okay. Okay, how about this? Let's just do a friction problem instead of a inclined plane problem, because I'm almost certain you're not going to get an inclined plane problem with friction. Not being cocky, but please do harder questions. Wow. Okay. Okay, I'll have to find one. Give me a second. Incline plane Regents physics. Okay, we'll do an inclined plane problem. So there's this question that I see here that says, okay, there are these three questions that I found. Okay, the first question says something like this. It says this. It's very easy. It starts out easy, but then it gets harder. So this first question says, three. Whoa, that's blurry. Sorry. Three. You have offended the teacher. Oh, Bajinder, I see your question. All right, so let me do your question, Bajinder. I'm sorry. Okay, let me do Bajinder's question, and then I'll do the question that was on the optional final. Okay, so I'll do that one. But let me do Bajinder's question first, and then I'll do the one that was on the final. So Bajinder's question says, a block weighing 10 newtons is on a ramp inclined at 30 degrees to the horizontal. So where's my pen? Whoops. So we have Fg equals 10 newtons on an angle of 30 degrees. A 3 Newton force of friction, F friction, equals 3 newtons, acts on the block as it is pulled up the ramp at constant velocity with force F, which is parallel to the ramp as shown in the diagram below. Okay, well, I don't really have a, I really don't have that diagram, Bajinder, so thanks for that. But I'm going to guess the diagram looks something like this. Here's my ramp. Here's my angle theta. Here is my box. And it's being pulled. Does it say it's being pulled up? Yeah, being pulled up. So with F, friction force is this way. We have Fg this way, and then we have F normal. So the first thing to do for these types of problems, with these incline plane problems, and it deals with friction, any type of force question, actually, it's always a good idea to draw a free body diagram, okay? Free body diagram. And what a free body diagram is what I just drew here. It's a dot with arrows coming out of it. So we have the force of gravity pointing straight down, the force F applied, pulling the block up, and then force of friction is moving in the opposite direction to the applied force. And then the normal force is perpendicular here. It's perpendicular to the surface, okay? So there's actually two other forces here. There's two other forces here that we have FG parallel and FG perpendicular. Okay, so basically the FG parallel is the force that's parallel to the surface. FG is the component of the force of gravity that is parallel to the surface. So that would be if this is my surface, right? then FG parallel is moving along this surface here, this incline. There's another thing that's parallel to the surface. The other thing that's parallel to the surface is F, right? So if we can solve for FG parallel, you find F, okay? The reason why we can make that conclusion is because of Newton's second law. Newton's second law says the net force equals mass times acceleration. But we don't have mass and we don't have acceleration, but we know that the net force is also equal to the sum of the forces. So that means that F net equals sum. This means summation. This sigma means you add up all the forces. Now, because these are vectors and we're in 2 dimensions, that means we need to have 2 components to the net force. We have F net y and F net x. So we have the net force in the y direction and we have the net force in the x direction. The net force in the y direction equals 0, okay? And the net force in the x direction also has to equal 0. Everything has to be equal to 0 because Bajender's problem says that everything's moving at constant speed, constant velocity. That means there is no acceleration. So that means that the net force in both directions equals 0. But because they equal 0, doesn't mean that the individual forces equal 0. They just have to add up to equal 0. So let's do that. So F net, let's look at the y direction. F net in the y direction equals my F normal force, okay? And it also equals my FG perpendicular plus FG perpendicular, okay? So the FG perpendicular is perpendicular to the surface. So that's this, that's this direction. This is FG perpendicular, okay? So FG perpendicular is given by, let me just give you the equations. So F normal is some value, and FG perpendicular is given by FG sine theta, okay? It's sine theta because perpendicular is a y component. So we have to use sine. We use sine for our y components, okay? So if F net has to be 0, right? That means F normal equals negative FG. I hope everybody sees that, okay? FG sine theta. We know what FG is. FG is 10 newtons. And sine theta is 30 degrees. So whatever this answer is, F normal equals the opposite of that, okay? F net in the y direction has to equal 0 because acceleration equals 0, right? If this equals 0 here, if this equals 0, then this has to equal 0, right? In an inclined plane, F normal equals FG or F normal equals F perpendicular. What are you saying, Bajender? Wait, it's cosine. Oh, yes, Bajender, you're right. Wow, second stamp. You're absolutely right, actually. This should be cosine. This should be cosine, cosine, cosine. Wow, I hate you, Bajender. This should be cosine. My bad. Cosine. Cos. 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 You're right. So that should be cosine. Okay, so let me write that up here. FG sine theta, and this should be FG cosine theta. You're right. FG perpendicular is cosine and FG parallel is sine. You're right. I'm so sorry. So we figured out the normal force. That doesn't matter. The question that Bajinder gave us, they want to know what this force F is. So we just have to do the same thing what we did with the y components, just to the x components. But now we have to replace it. So I'm just gonna why is it doing that? Anyway, I'm just gonna let me fix this because this is getting annoying. Okay, so they want to know the x components. So we have F net x equals F friction plus, okay, Anisha, I'll get it together, my bad. So F friction plus F G parallel plus F. Okay, there's these three forces in the x direction. You have the friction force, which they give you. They have this force that we're trying to solve for, and then they have FG parallel. Yeah, so Bajinder, the normal force on a inclined plane equals F perpendicular, FG perpendicular. Okay, whoops. What the hell is going on? All right. Okay. So we're going to plug in these values. So F net x, remember, is 0 because it's moving at a constant speed. Naya, I'll draw the guide in a second. It's moving at a constant speed, so F net has to be 0. Remember, if acceleration is 0, then F net has to equal 0. So friction is given. Friction is -3 newtons, right? We're just going to give it a negative value because it's in the opposite direction to our force and our parallel force, okay? FG parallel is given by this right here, which is FG sine, so that's 10 newtons times sine 30 degrees, and plus F, which is what we're solving for. So I don't know what 10 sine 30 is. Can someone figure that out and tell me, please? I don't know what the hell that equals. Let me just figure it out. 10 sine 30. That's not correct. 5. Oh, it equals 5. Thanks. Okay, so we got 0 equals -3 newtons plus 5 newtons plus F. Okay, so -3 plus 5 is 2 newtons plus F. We got 0. So that means that F equals -2 newtons. Okay, I might have done something wrong, but whatever. Okay, so the magnitude is 2 newtons. So I guess the answer is 2 newtons. Is that correct, Bajinder? I don't know. in an experiment, a 0.02 kilogram rubber stopper. Yeah, so Abdullah, it says, oh, it's 8 newtons according to them. So, okay, so I can see why it's 8. That means that this should have been positive, this 3. So then if we add them up, then this would be 8, all right? So that means that the direction here doesn't really matter in that case, because I actually drew it thinking that the incline was over to the right. We could have drawn it this way, right? And then the friction force will be pointing this way. So I guess they just ignored the direction of the vectors, so that's fine. So the answer is 8 then. If they say it's 8, it's 8. Okay, so let me answer Anthony's question. In an experiment of a 0.025 kilogram rubber stopper is attached to the end of a string, a student whirls the stopper overhead in a horizontal circle with a radius of 1.0 meter. The stopper completes 10 revolutions in 10 seconds. Determine the speed of the whirling stopper, please. All right. This is going to be very interesting. So we have a mass of 0.28 kilograms. We have a horizontal circle radius equals 1.0 meters, and we're also given number of cycles equals 10, and time is 10 seconds. So, wait, what's the question asking for? Determine the speed of the stopper. Okay, V. Okay, so in this case, we have some type of circle like this, and we have the radius here, R, and we need to figure out what to do with this number of cycles over 10 seconds. So speed is given by distance over time, okay? The distance traveled around a circle is the circumference, right? The distance traveled around a circle is the circumference. So in order to figure out the circumference, in order to figure out the distance, we need to replace distance with circumference. And I believe the circumference is 2 pi r for a circle. Okay. And instead of time, we use the period. Period is given by the number, how long it takes to go around the circle one time, okay, to make one revolution. So it says it makes 10 revolutions in 10 seconds. So that means in order to go around one time, it takes 1 second. So the period is given by the time over the number of revolutions, which is 1 second. Okay? So 2 pi r, we have, I don't know what, 2 times 3.14 times the radius, which is 1 over 1. So that means it's 2 pi, basically. That's what the answer is, which would be 6.28 meters per second. Is that correct? Okay. I just wanted to clear up something that Fazia asked. Fazia, you asked if sine is the x component and cosine is the y component. For projectile motion and for all other things, sine is the y component. So sine is y component and cosine is the x component. Okay? This is for everything except for inclined planes. Okay? So everything except inclined planes. Okay, everything except inclined planes. For inclined planes, sine is your x component, or what's considered your parallel component. Okay? And cosine is your y component, or your perpendicular component. Okay? So this is for inclined planes. For inclined planes, planes only. All right. So I did projectile motion. I did inclined planes. I think Sadia wanted me to do a absolute index of refraction question. Da, 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 da. Okay. If you guys have any questions, like what Bajinder and Anthony have been doing, posting them in the comments, you guys can post them, and then I will do that. Okay. So let me see if I can find an index of refraction question, which would be wave phenomena. Okay, so there's this question here. Whoops. Okay, so I found this question. It involves the absolute index of refraction. Okay, so this is the question. It says, base your answer on the information and diagram below. Oh, yeah. Whoops. I totally forgot about the optional final. Okay, okay, okay. Sorry, Alexis. Okay, let me do the optional final question first, and then I'll do I'll do these other questions. My bad. Let me get that question. Kind of messed up there. Okay. Okay. So the optional final says a horizontal 20 Newton force is applied. Let me get this thing here. This is what the question looks like. A horizontal 20 Newton force is applied to a 5 kilogram box to push it across a rough horizontal floor at a constant velocity of 3 meters per second to the right. Calculate the coefficient of kinetic friction between the box and the floor. So, so I'm going to list out my variables. A horizontal Newton force. So this is applied. F applied. FA equals 20 newtons. And it's applied to a 5 kilogram box. That's my mass, 5 kilograms. Okay. To push it across a rough horizontal force. So during Regents Prep, I mentioned the word rough automatically should click in your head and say something like rough means friction. Okay. If you saw the word smooth, you should automatically know it's frictionless, but rough means friction. This word means friction. Okay. The speed is 3 meters per second to the right. The speed is 3 meters per second. Now notice it says constant velocity. It says constant velocity. That means that acceleration equals 0. Okay? So that means the net force equals 0. If the acceleration equals 0, that means the net force equals 0. Since F net equals mass times acceleration. If acceleration equals 0, F net equals 0. So that means the object is in equilibrium. That means all the forces have to be balanced. So just to recap, if speed is constant, then A equals 0. If A equals 0, then F net equals 0. If F net equals 0, then object is in equilibrium. And then lastly, if the object is in equilibrium, that means that Newton's third law is like very dominant here. That means that all the forces are equal and opposite. So if the object is in equilibrium, that means FA equals negative FB, basically. Okay. Okay. So just to go back to the problem, these are all different bullet points, okay? And we have this, this is true for this problem. Just because of this word constant velocity, this we can assume, all of this. So in order to calculate the kinetic friction between the box and the floor, we need to use the only equation where the coefficient of friction appears. Coefficient of friction is given mu. Okay, this is what we need to solve for. The only equation in the reference table that uses this is F friction equals mu times the normal force. Okay, I mentioned in a previous problem, anytime we're doing something with forces, we want to draw a free body diagram. So to draw a free body diagram, hold on, let me just make this a little bit smaller. We want to do a free body diagram. My free body diagram looks like this. Here's my box, here's my floor, here's my box, okay? And my free body diagram, I have FG pulling down on it, the weight, okay? I know that there's weight to this box because the problem gives me a mass. FG in this case equals mass times the force of the acceleration due to gravity, which is approximately 50 newtons, okay? Because if I estimate G equals 10 meters per second squared. F normal, Fn, F normal. According to this, since the object is in equilibrium, Fg has to be equal and opposite to F normal. So that means F normal also has to be 50 newtons. Okay? So now we're done with our y components, right? 50 and 50, it's done. We've shown that it's in equilibrium. We have two other forces here. We have the F applied force, and then we have F friction. F applied is 20 newtons. That's given in the problem. That means F friction has to be 20 newtons as well. Why is it 20 newtons? Because of this rule right here. If the object is in equilibrium, then these forces are equal and opposite. So now we can plug it into this equation right here, right? F friction is 20 newtons. Mu is what we're solving for. And F normal is 50 newtons. So we solve for mu by dividing 50 newtons on both sides. And we get mu is approximately 0.4 nothing. The units cancel out, okay? It's a coefficient, so this is the answer. That's the answer to part one, Alexis, all right? Mu equals 0.40. If you actually used like g equals 9.81 instead of 10 meters per second squared, then you'll get mu equals 0.41, which is also the same. Okay. The next part of the question asks, determine the magnitude of the force of friction acting on the box. Well, we figured out the magnitude of the force of friction acting on the box because we did it right here. So the force of friction acting on the box is already done. Done. Okay. So okay, let me go back to the let me go back to this question here. Oh, wait. I think Anthony posted a question. Let me do this question first, then I'll do Anthony's question, and then I'll do Abdullah's question. All right. So this question here, this one says, a ray of monochromatic light of frequency that hertz is traveling from water into medium X. The angle of incidence in water is 45 degrees, and the angle of refraction in medium X is 29 degrees as shown. Calculate the absolute index of refraction of medium X. Show all work, including equation and substitution with units. So when we're given two angles and two different mediums, the equation on the reference table to use is this equation. It's called Snell's law. And basically what this is saying is you have some medium and the angle of some light ray equals the next medium and that angle of that refracted light ray. That's what that is basically saying, mathematically at least. So N1 is our first medium. N1 is water. This is what N1 is. N1 or water in our reference table, I think water is 1.33. So 1.33 is N1. Sine theta, our angle for theta 1, our angle of incidence is 45 degrees. So times sine 45 degrees. I'll have to have someone do the math for this and then let me know what it says. N2 is medium X. We don't know what it is. That's what we're solving for. That's calculating the absolute index of refraction. That's N2. And sine theta 2 is 29 degrees. So sine 29 degrees. So let me actually see if I can do this. We'll have 1.33 times sine of 45 degrees. So on the left side, I have something like 0.94 equals N2 and sine 29. Did someone put it in there for me? No. Sine 29 equals 0.485. And so I'm going to have N2 equals 0.94 divided by 0.485. And that is 0.94 divided by 0.485 equals 1.93. So that gives me an index of refraction of 1.94. So the index of refraction for medium X is 1.94. Okay. Oh, thanks, guys. Okay, so this is a pretty simple problem. It looks a little bit challenging because we didn't get to go over it in class, but that's the work for it. Okay. I see that you guys posted another question here. It says a light ray traveling in air enters the second medium and it slows to 1.71 times 10 to the 8 meters per second. What is the absolute index of refraction for the second medium? Okay, so for that one, let's see if I can do that. That says traveling air enters a second medium. So N1 is air. N1 for air would be 1.00. And it says that the speed is 1.71 times 10 to the 8 meters per second. So this is V1. I mean V2. This is V2. That's V2. The reason why it's V2 is because this is the second speed. This is the speed after it has passed through air. The speed V1 when it's in air is 3 times 10 to the 8 meters per second, right? This is on your reference table. This is the speed of light in a vacuum and the speed of light in air, 3 times 10 to the 1. So that's V1. V2 is the speed. So under waves, you'll see like an equality where it's like n1 over n2 equals v2 over v1, something like that. It's on page 5, I think. Yeah, page 5. And the equation looks like this, where it's n2 over n1 equals v1 over v2 equals lambda 1 over lambda 2. Okay? So what we're going to do here is we're going to pick which ones we have. We don't have lambda, so we don't need to use this part of the equation. We just need to use this part, okay? So N2 is what we're solving for, N2. N1 is air, that's 1.00. V1 is you have to assume the speed of light in air, which is 3.0 times 10 to the 8 meters per second. And V2 is the slowed down speed, which is 1.71 times 10 to the 8 meters per second. You solve this and make sure these are in parentheses. Any exponent should always be in parentheses. Make sure that's in parentheses and you should get your value. Okay? Oh, what just happened? Whoops. Okay. Code red. Okay, hold on. It really did just like shut down. Okay, it's back up. So sorry about that. What I said, I guess, when the video went down was this part here, which was lambda 1 over lambda 2, is not necessary because you're not given wavelength. Nobody cares about wavelength for this part. They just gave you absolute index of refraction and V1 and V2. So this is the formula that you use and you substitute here. Make sure that these numbers are in parentheses, okay? So I don't really know what the answer is. I don't have a calculator on hand that can put in. I don't have a calculator on hand that can put in those values very easily. So you guys can figure out what N2 is. All right. Okay. What was the next question you guys wanted me to answer? Someone just post. One person, please post a question, because I don't want to scroll through all that. Can you please do the more recent topics we didn't do in class? Yikes. Naya, you okay? Give me a second. Let me just pull up some stuff. Okay, so these are some of the things that we didn't go over in class. You ignored me more than Alexis. Whoa, wait, I was next. Thanks, French. Hello. Give the ladies a chance, Abdullah. Which type of photon is management? Okay, so let me just go over that. Let me just do a quick thing, because I said that I was gonna end this at 9 o'clock. And I mean, I got stuff to do and I don't want to spend all night doing Regents prep. It's been nice, but I got things to do. So we have like 30 minutes left, and there's 2, 3, 4, 5, 6, 7. There's like 7 things we didn't go over about modern physics. All right, and I'm gonna just say copy and paste this. So these are the stuff that we didn't get to go over. Okay. These are all different stuff. 1, 2, 3, 4, 5, 6, 7. So the dual nature of electromagnetic radiation. What that means, another thing you'll hear, the dual nature of electromagnetic radiation is the wave particle duality. What that means, basically, in very, very, very basic terms, is that light behaves like light behaves like a wave and a particle at the same time. Okay, I don't know if me writing this out is even helpful, but I'm gonna do that anyway. Okay, so what are some things that represent or characteristics of light that indicate that it behaves like a wave? Some characteristics that show that it behaves like a wave. So these are wave characteristics. So wave characteristics are, there's a few wave characteristics. If the object can refract, meaning bending waves, okay? If the object can refract, it is a wave. If the object can diffract, diffraction is scattering waves. You know, like how some of you guys live with like cockroaches in your house? Well, when you turn on the lights, like the cockroaches scatter, that's like waves, okay? So that's what diffraction is, scattering cockroaches. Anyway, another wave characteristic is interference. Interference, you have both constructive and destructive, okay? Destructive. If you can add 2 waves together and they become a larger wave, or you take one positive wave and a negative wave and they destroy each other, then it's a wave, okay? Particles can't really, well, I guess they can add together, like they fuse, but not the way that waves can, okay? There's something called the Doppler effect. This is something we did not go over, okay? The Doppler effect is named after somebody, but it's a shift in an apparent frequency, okay? So for the Doppler effect, basically it's a perceived shift. It's not something that actually happens. It's all perception. So it's the type of thing that you guys will hear when like a truck passes by. It has like a high-pitched sound as it's coming towards you, but then it has a low-pitched sound as it goes past you. So if this is you, the observer, okay, that's you, and then this is the truck over here, and it's blowing its horn, okay? As it's approaching you, it's going to have a higher frequency, right? But after it passes you, it's then gonna have a lower frequency. So this is apparent, parent, meaning that it's perceived. This is not always true. I don't know if that's how you spell perceived. That's not always true, but it's just something that people will experience, right? So yeah, that's really all I have to say about the Doppler shift. So it's like an ambulance passing by or a truck, and it'll be like very, very high, and then it'll go really low. So it'll be like, "Ew," like that. Okay? Don't laugh at my sound effects. So this observer, this person right here, will observe a higher pitch, which means frequency. Whoops, frequency. Higher pitch as it's approaching, and this would be a lower pitch or frequency as it moves away. Whatever the opposite of approaching is. So higher pitch frequency when the object is approaching, the wave is approaching, not the object, the wave, sorry, and lower pitch when the wave is leaving you. All right, so that's what the Doppler shift is. Okay. The last thing, well, that's about it, actually. There's also something, if I go back up here, some other things that include wave characteristics, something called the photoelectric effect, the Compton effect, and black body radiation. Black body radiation, this this is kind of like misleading, I guess. Black body, something that's a black body just means it's what physicists use for something that's very, very, very hot. Okay, so when you hear something like black body, maybe it'll be on the Regents, maybe it won't, but something that has a black body radiation means it's just very, very hot. So the sun gives off ultraviolet radiation. It is a black body. Even though it's not black, it's very actually it's very bright. Like you can go blind looking at it, but it's considered a black body because it gives off it gives off it gives off a lot of high energy radiation. So black body just means something very, very hot. So black body, something very hot. Okay. Photoelectric effect. The photoelectric effect is another thing that is a wave characteristic. The photoelectric effect is given by this equation. E photon equals, what is it? Planck's length times frequency, and it also equals hc over lambda. This is the photoelectric effect. Photoelectric effect. The photoelectric effect is basically so this has to do with something that each photon, the energy of each photon, basically, right? That's why this you have here, the energy of each photon. And there's this word that you'll probably see, maybe you won't see it on the Regents. It means quantized. Quantized means like tiny, discrete, specific amounts. So this means discrete or specific, right? And this is actually very related to the hydrogen and mercury atom and excited states and all that nonsense, where electrons and atoms are very specific and the amount of energy that they want to absorb. So, or the amount of energy that wants to be quantized, it needs to be specific, it needs to be discrete. The electron will not take certain amounts of energy. It can only take, the electron will only take certain amounts of energy. And usually it's in the form of the photon hitting the atom, okay? So yeah. there's a nice like animation that I like showed the students last year. If this is your nucleus and you have like orbitals around the atom, okay? You have these electrons around the atom. Let's say, I don't know what atom this is, but let's just say you have something. This is probably not very accurate, but let's say that you have a photon coming in. Okay, this is a photon. You have a photon coming in, and what's going to happen? It's going to excite this electron, and this electron is going to jump to a different orbital. Okay, it's gonna leave this area and move to another one. That's the photoelectric effect. When a photon comes in, excites the electron, it meets the discrete and specific value the electron needs, and it will jump to the next level. It's moved to an excited state. That's the photoelectric effect. Okay. What's next? Compton effect. Whatever. That's not important. So that's basically this. Those are basically characteristics of waves. Okay. I'm sure you guys remember some characteristics of particles. And some characteristics of particles involve like that they attract each other and they I don't know, that they have momentum, they have mass, they I don't know. The characteristics for particles, I guess, is a little bit more harder to explain. It's basically everything you've learned in like chemistry and physics up until the modern physics, that you can like dissolve particles, you can like mix them. You can't really mix waves, you can't dissolve a wave, you can't like dissolve light. I haven't done quarks yet. Who is that? Mr. Redman 1998? No, I haven't done quarks yet. But particles you can dissolve, you can accelerate them, there's a force of attraction between them. Waves don't have that. Waves don't have forces acting on them. Waves cannot be dissolved in like a glass of water, right? Particles can. You can take sugar or salt or some other type of dissolvable powder and you can dissolve them. You can also crush particles up, right? Make them smaller. Or you can put them together and make them bigger. But you can't do that with waves. You can't dissolve a wave. You can make them interfere, but that's not the same thing. Hi. You cannot do the same thing with waves that you can do to particles. However, this phenomenon, the wave-particle duality, light can do that. Oh, I guess I accidentally said you can't do that to light. Sorry. Light, you can do that to light. You can dissolve light. You can take like the photons and dissolve them. You can take them and mix them together. You can take them and split them apart. You can also refract and diffract them and do all that. Okay. Okay, so let's move on. I hope that's okay. The next thing is what did I say the next thing was? The next thing was the quantum nature of atomic energy levels. Oh boy. I guess this is what Abdullah was asking for. Okay. So before we can talk about like the quantum levels of energy and atoms, we need to talk about the different models of the atom. And I think like you guys are accustomed to very, very like wrong models. But there's two models, I guess you'll know. The two models are the Rutherford model and the Bohr's model. Okay, maybe you learned both of them in chemistry, hopefully. If you didn't, then that sucks. So the three things for the Rutherford model is that atoms are small and massive. So small, massive, positive nucleus. That's the first thing. The second thing for the Rutherford model is that electrons orbit the nucleus. The third thing is that most of the atom is empty, right? Most of the atom is empty space, okay? This model, however, it wasn't completely wrong. It was just incomplete. So it was missing some things. The Bohr's model mentions some things. One thing Bohr mentions is that electrons don't lose energy as they accelerate. It means instead they're what's that word? Quantized. You have quantized energy levels. Energy levels for electrons. So basically this means that electrons in their orbitals or in their places in their orbit can only exist there when they're given specific discrete levels of energy. So electrons are constantly accelerating usually in the form of centripetal acceleration. Electrons can move in a straight line. They can move in curved trajectories. They move at a random nature. Sometimes they can teleport. They can move from one spot to another spot. So electrons are very unpredictable. That's why in the current model of the atom is that it's a cloud. It's not like some circular orbit or elliptical orbit like how the planets orbit. It's actually a cloud. So in order for those electrons to move around, they seem to need to like lose or gain energy, and that's not true. The electrons somehow just keep their momentum and keep their energy. So that's what that means. Okay. The second one is that I think this one has to do with specific orbits. So specific orbits or orbitals for each atom. So that means every atom can only have like at every energy level specific orbitals. Okay, that's something you learn in chemistry as well. I'm not going to go over that. And in order to change energy levels, right, in order to change from one orbital to the other, they have to absorb or emit a photon. So to change or to jump, I'll say, to jump from one orbital to another, the electron must emit or absorb a photon. Okay, and it needs to be a specific energy. That specific energy for that photon, right? This specific energy needs to be E photon equals E initial minus E final. Okay, so the difference between the electron's initial energy and the final energy has to be exactly equal to the energy of the photon. Okay, so that's the Bohr's model, I guess. So if we have, no, I don't want to do an equation. So anyway, Bohr, I think he won like the Nobel Prize for like finishing Rutherford's model. And currently we use like the Bohr's model, but the Bohr's model is also not complete. It's missing some information. So that's that. Science is ongoing. So under here also is the energy level diagram stuff on the reference table. Okay. And if I don't know if you guys have your reference table available, but I'm looking at a picture of a reference table. And on the hydrogen side, if we're interested in a hydrogen atom that's moving from, you know what, let me get a picture of the reference, the hydrogen atom for you guys right now, actually. if we're looking at this hydrogen atom, okay, and we want to, the question is like, an electron in a hydrogen atom drops from the N3 state to the N2 state, and we want to determine how much energy is emitted. How much energy is emitted as radiation? That would be the question, right? So the question could be, how much energy is emitted as radiation? What they mean by radiation is how much energy is emitted as light. Radiation is light, okay? So is there going to be a French's model? No. How much energy is emitted as radiation? So what's the energy of the photon? Because light is photon. So we're going to use this equation that we wrote down up here. E photon equals E initial minus E final. So let me change the color. I don't like writing in red. So E photon equals E initial minus E final. So E photon is what we're solving for because that's radiation, okay? So E initial is N3. This is my initial, right? Because we have an electron that's jumping from that orbital to this orbital, from the N3 orbital to the N2 orbital, the N3 level to the N2 level. So we're going to do negative 1.51 electron volts minus negative 3.4 electron volts, and we get this is plus, what do we get? We get, I don't know, let me do this really quickly. This is 3.4 minus 1.51, we get 1.89. So the E photon equals 1.89 electron volts. So that would be the answer. So the energy emitted as radiation, or the energy emitted as light, or the energy emitted by the photon is 1.89 electron volts. Okay, so that's basically that. All right, where were we? What were we talking about after that? We did the models of the atom, we did atomic energy levels. Oh, conservation laws. I just need to mention something about conservation laws. There's a lot of different conservation laws, but I'm just going to write down the conservation laws that are going to be present on the Regents that they may ask you for. Okay, you have, these are conservation laws. So you can conserve mass, you can conserve energy, you can conserve momentum, and you can conserve charge. Okay, those are the 4 things we learn in Regents physics. These 4 quantities are conserved. In modern physics, they found out that energy and mass are actually the same thing. So there's something called mass energy equivalence. And so the conservation of mass energy is what it would be called. Okay, so mass and energy are the same thing. Conservation of momentum is given by P initial equals P final, right? Conservation of charge is Q total initial equals Q total final, right? Conservation of mass would be mass initial equals mass final. Conservation of energy equals E initial equals E final. That's conservation of energy. Conservation, or this mass energy equivalence here, this is given by an equation by E equals mc squared. Okay, this is Einstein's famous formula. It's in its incomplete form. This is a incomplete form that everybody like recognizes and knows, but the E represents energy, M represents mass, and c represents the speed of light. So this is like a theoretical thing. There is no real application of this yet, but your question you could be asked is something like this. You could be asked a question like this: what is the energy equivalent of 1 kilogram of matter? And in order to do that, we just use this equation. So the energy equivalent of 1 kilogram, that's my mass, 1 kilogram, times the speed of light squared, 3 times 10 to the 8 meters per second squared. This is 9 times 10 to the 16 joules. Energy is joules. So the equivalent energy that 1 kilogram of mass of matter can turn into is a lot. This is I think more than enough energy to power the United States for like a long time, the entire country for a long time. So this is that 1 kilogram is converted to a lot of energy. Okay, but that's only when the object is accelerated to the speed of light. All right. Okay. If you want to learn how to derive that equation, Bajinder, you can take some physics in college. When you take some quantum physics, you'll learn about the rest of this. This E equals mc squared has some other terms present there, so you'll learn about that. Okay, so what's next? We did E equals mc squared. There's something called binding energy. We don't really need to know too much about that, but the binding energy, I'll just give it down for completion's sake. Binding energy is what really keeps things together. Okay, binding energy. If anybody's like familiar with the Death Star from Star Wars, the Death Star works in that the Death Star is able to match the energy, the binding energy of a planet. That's how it's able to destroy planets. So it's able to match and overcome the binding energy of a planet. The binding energy is given by E binding equals delta m c squared. That's what this is. So it's the change in mass that we wanna remove, right? So this is E equals mc squared. It's the same thing. Okay. Some other things I guess we should have gone over is fission and fusion, but I think you guys know how fission and fusion work in chemistry. Fission is splitting an atom, and fusion is putting two atoms together. All right. So now I want to move on to what I think Jared just finished asking in the comments. It says hadrons and leptons. So there's something called the standard model of particle physics. Okay, standard model of particle physics tells us that there's basically two things in the universe: matter and antimatter. Okay, and we've kind of like grown into the world of matter. Matter is everything we see, right? Our universe, our whole planet, me, you, everyone, everything is made up of matter. Antimatter is like the evil twin of matter, and they exist. Scientists have created it. When I was doing some labs, I created some antimatter as well. So for every particle in the world, there's a evil twin or an antimatter counterpart. Okay. So so let's say you have a proton. Proton is matter. The antimatter is something called the antiproton. Okay. If you have an electron, the antimatter is the anti-electron. anti-electron actually has a specific name. It's called the positron. Maybe you've heard of it in chemistry or middle school. I think that was the earliest I've heard it, in middle school, the positron. And I didn't actually believe my teacher because it didn't make any sense to me. This one's kind of confusing. There's a neutron. That's spelt wrong. Neu, I think. Okay, let me just rewrite that. Neutron. That's the matter. Now the antimatter version of the neutron is called the antineutron. Now this is kind of confusing because matter and antimatter, the way you can differentiate the two is just by the charge of the object. So a proton is +1. An antiproton is -1. An electron is -1. An anti-electron or positron is +1. A neutron is, you could say it's +0, right? And the antineutron you can say is -0. So it's still 0, but there is something called an antineutron. Okay, it's really strange. So antimatter, let me just write this down. Antimatter has the same mass as matter, except the charge is opposite. So the proton has some mass. It's given on your reference table. The mass of a proton is 1.67 times 10 to the -27. That's the mass of a proton. The mass of an antiproton is the exact same, 1.67 times 10 to the -27. The mass of the electron is 9.11 to the -31. The mass of a positron is 9.11 times 10 to the -31. The only difference between matter and antimatter is their charge. Okay, they're exactly the same. They look exactly the same. The charge is just different. There are other particles called neutrinos, there's antineutrinos, there's quarks, there's antiquarks, there's mesons, there's antimasons, hadrons, antihadrons. So there's literally antimatter for everything. And antimatter and matter are created equally together at the same time. So let's say you take two particles and you smash them together. There'll be an explosion and light will be created. And what will happen is that you'll have, let's say, an electron and a positron being created. Okay, they're always created in pairs. But when you take an electron and you combine it with let's say, a positron, you put them together, what ends up happening is that the matter and the antimatter cancel each other out and they eliminate each other in a big explosion. They destroy each other, something called total annihilation. Annihilation. Okay, this is actually a very scientific word, annihilation. Okay, so that's about it. That's about it about matter and antimatter. So now I need to go on to this next page of the reference table. Let me see if I can just get this darn image in here. So this is the image you'll see on your reference table. It's matter, right? And I think I mentioned it one time that there's an identical amount of matter. Actually, you know what? I just finished reading this. I just finished reading something. Dwayne says anti-Dwayne. Yes, theoretically, somewhere in the universe, or maybe in a parallel universe, that there exists a version of Dwayne and a version of everyone that is completely made up of antimatter. So the issue is if Dwayne and anti-Dwayne ever touch each other, they would destroy everything. Because remember, 1 kilogram gets converted into 10 to the 16 joules, which is 100 million million. Okay, so that's a lot. That's a large amount of energy. That powers the whole United States. Dwayne is about, let's say, 60, 70 kilograms. If Dwayne and anti-Dwayne touch each other, that's 60 kilograms times 2. That's 120 kilograms that would be converted into energy. That amount of energy, let me do that really quickly. E equals mc squared. So that's 120 kilograms times the speed of light, so squared. So let's see what that is. 3 times 10 to the 8 times 3 times 10 to the 8 times 120. So my calculator is giving me a lot of crazy stuff, but I see 1.08 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, I can just do that. It's 18. Duh. 18 joules. That's a lot. That's billion, billion, billion. So that, I think, would like destroy the country. Okay? So Dwayne and anti-Dwayne converting into energy would destroy the whole United States. So basically, Dwayne is a terrorist. All right. I just want to move back onto this particle physics. Okay. So matter is classified into two different things: hadrons, which are considered the heavy particles. Heavy are hadrons, and leptons are the light particles. Leptons, some examples of leptons are electrons, positrons, and neutrinos. Okay, these are tiny particles. Electrons are very tiny, right? Uh, they're so tiny that you really can't even see them under a microscope. Neutrinos are even tinier particles that actually pass. They're so tiny that they don't interact with matter. They pass through most of you all the time. Neutrinos come off from the sun and other types of radiation. And there's neutrinos that are like passing through things all the time, but they're so tiny they never hit anything. If a neutrino did hit you, it could cause like mutation, but you never get hit with a neutrino because it's so tiny. Okay, so that's that. Hadrons are further broken down into these two these two particles: baryons and mesons. Okay, baryons are your protons and neutrons, and antiprotons and antineutrons. Mesons, I think I went over some of these in class. You have your pions. You could have a positive pion, you could have a negative pion, and you could have a neutral pion. There's also something called kaons. You could have positive, negative, and neutral. There's also something called tauons, I think, tau particles. You could have positive, negative, and neutral. Okay, there's a lot of mesons. And there's a lot of baryons as well. I'm not going to go over all of these different things, but just know that the smallest particle in the universe right now are these things called quarks. Okay, quarks make up everything except for leptons. Leptons can't be broken down any further, but quarks can make up other things. So you have are you guys have a question for me? I know there's like this lag that's so annoying, but I see that you guys are having some type of question. Oh, you said mass can be created basically. Yeah. So there's this idea that that you guys have been told and you probably heard that you can't create mass, or you can't create energy, you can't destroy energy, you can't destroy mass. That is true. The only exception is when antimatter and matter meet each other. Okay? What happens is that the energy gets destroyed, not completely. I mean, it gets destroyed is that it disappears. It literally will just disappear and turn into energy. That's all it means. Okay? So sorry. It's just a simple explanation. So it just converts to energy. But it's the idea that mass is actually being destroyed. And that's true. Okay? So we were talking about quarks. Okay? Something about quarks is that quarks exist in threes or as a quark and an antiquark. Antiquark. Okay? Quarks exist, they can never exist alone. So this means that quarks cannot exist. Quarks cannot exist alone. They're always in either pairs or threes. So for baryons, is that what they are? Yeah, baryons. Quarks need to be need to come in threes. So for a proton is a baryon. Baryon. And that means it must have 3 quarks. The way I was doing it in Regents Prep is that this is a proton and it has a charge of +1. And so therefore I must have 3 quarks. Okay? 3 quarks. Now the 3 types of quarks depend on what type of particle it is. Protons are a first generation particle. So that means you use the first generation quarks. Okay? That means where's my quarks here? Copy. So these are my quarks here. My first generation quarks are this right here. Okay, you're going to be told on the Regents explicitly when a particle is first generation and second generation or third generation. All right, you don't have to memorize it. The only thing you have to know is that for the most part, quarks don't go across generations. Sometimes they do, but for the most part, they don't. All right. Quarks, if you notice, are fractions of the elementary charge. So that means if a proton is +1 and we need 3 quarks to make a proton of +1, we need to have up, up, down to make a proton. Okay? The reason how we know it's up, up, and down is because up is +2/3, up is +2/3, and down is -1/3. This equals +1, +1. Okay, so this is the charge of a proton, +1. So therefore, these 3 combinations equal +1 when added together. So the way you'd write the quark configuration or the makeup of a proton is up, up, down, UUD, UD. Okay. For a neutron, let's go down to a neutron. A neutron, this is what the neutron looks like, and it has 3 quarks because it is a baryon. A neutron is a charge of 0. Q equals 0. So we need to figure out what 3 combinations add up together to equal 0. Well, it's up, down, down, up, down, down, ud, ud. So this is +2/3, -1/3, -1/3, right? This is -2/3 +2/3. This equals 0. So this is the quark makeup for a neutron. All right. If we wanted to do, let's say, an antineutron, antineutrons need to be made up of antiquarks. Okay, antiparticles need to be made up of antiquarks. So we have Antiparticle, antiparticle, antiparticle. You signify an antiparticle with putting a line or a bar on top of them. All right? So it's the same makeup, there's just the opposite particles. Up, down, down. The way you'd say it is anti-up, anti-down, anti-down, which is negative 2/3. Remember, for antiparticles, we have the opposite charge, plus 1/3, plus 1/3. This still equals 0. Okay? The signs were just switched around. So that's the antineutron. If we wanted an antiproton, antiproton, you had up, up, down. Well, an antiproton needs the opposite particles, which are the antiparticles. So anti-up, anti-up, anti-down. So anti-up, anti-up, anti-down, which equals negative 2/3, negative 2/3, positive 1/3, which equals negative 1. So the charge of an antiproton is negative 1. All right. Now I'm just gonna do this just to show you guys. We have an electron, and if we want to figure out the quark configuration for an electron, well, the electron is under here is a lepton. If we look under leptons, we don't see that leptons are made up of quarks. So therefore, electrons are fundamental particles. Fundamental means basic or smallest. Okay, electrons are the smallest particles you can have, just like quarks. Quarks are fundamental particles. Protons and neutrons are not fundamental because they can be broken down further. Okay, so electrons are fundamental particles. Therefore, electrons don't have quark configurations. All right. Okay. I want to do some mesons now, actually. Mesons, okay? Mesons are different than baryons in that you need one quark and one antiquark. So therefore, if we look at a positive pion, okay? Positive pion has a charge of +1. So, and we need 2 quarks. We need one quark and one antiquark. To get +1, let's say that this pion is a second generation particle. That means that we have to use charm and strange. Hi. Thank you. So second generation particles, we have to use charms and quark, charms and strange. So we have a +1, and we can use a charm, which is +2/3, and we can use an anti-strange, which is +1/3. A strange is a -1, but an anti-strange takes the opposite charge, which is +1. So this becomes 3/3, which equals +1. So charm and strange and anti-strange equal the quark configuration for a positive pion. Okay. The Regents to Mars in the afternoon, I think it's 12:30. So, oh wow, it's like after 9 o'clock. 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 6. Okay. I can go until 10 o'clock, but then after that, I think I have to go because I do want you guys to make sure you guys get at least 6 hours of 7, what did I say? 8 hours of sleep. 8 hours of sleep. Okay. So if we wanted to do a negative pion has a charge of -1. A negative pion is a second generation particle. So therefore, we need to use charm and strange. For -1, we're going to do a strange and an anti-charm. Strange is -1/3, and anti-charm, charm is 2/3, anti-charm is -2/3. This equals -1. Okay, so this is the core configuration for a negative pion. Okay, I think you guys can figure out the rest of the other quarks, like the negative negative kaon and all those other stuff. Okay, there's a question here. Let me put it up for this. This is a question that was asked a few years ago. This question is this. Wow, sorry that it's so bad. But these are different choices. This is 1, 2, 3, and 4. The question says, compared to the mass and charge of a proton, an antiproton has one of the following. So the mass of a proton and antiproton should be the same mass. So that means 4 is eliminated and 2 is eliminated because it talks about greater mass. So it's either 1 and 3. And we're talking about a proton and its antiparticle, the antiproton. Well, the answer has to be 3 because it says opposite charge and same mass, okay? The one thing to remember about the antimatter questions is that, or antimatter in general, is that it has the exact same mass. It's identical to the matter except for the charge. The charge is opposite. Okay. That's pretty much it about particle physics, or modern physics rather. K-pops. Same mass, different charge. Mr. French, did the teachers put their grades in? I think our grades are due on Thursday, unofficially. That's off the record. I'm not supposed to say that, but the grades are due on Thursday. Okay, so do you guys have any questions? Anything else you want me to review, go over? I think you guys are in good shape. What I did today, actually, for the Regents prep was, after Regents prep, actually, today, in school, I wrote down everybody's name on the board, and then I wrote down a prediction as to what grade I think they're going to get. And it's based on how you guys did in previous exams. Okay, well, if you guys don't have any like questions relating to physics, I'm gonna mute my microphone. I'll still be on this chat for like a few minutes until 10 o'clock. So if you guys have any questions, you can put it in the chat and then I'll draw it out for you guys, okay? But other than that, thanks for coming. Make sure you guys get something to eat tomorrow, especially if you're taking an exam in the morning, okay? I don't think a lot of you guys are, but if you're taking the exam in the morning, make sure you get something to eat. You will not be able to perform without brain food. And I would suggest that you avoid like fatty foods, avoid salty foods, and avoid like sugary foods. So eat something like natural, something that's not like, doesn't have preservatives in it, something that doesn't have sugar, because it'll just like make you crash, okay? So try to eat something, try to get some like sleep, don't do a lot of cramming, because I wrote in the email is that cramming, you don't get to retain a lot of that information. So just go over that Regents prep guide that I handed out in class, and I think you guys are going to be good. I don't know if I'm going to be able to see you guys before the test, but I think I may be in either Mr. Wellington's room, room 103, or Miss Tassiela's room, room 112. So if you guys want to like come, and I'll give you guys like some like last minute tips or any questions you guys have, then you can come to that room. Okay, so I'm going to mute my microphone. Thank you for coming. Good luck. Good night. If you still have any questions, I'll be here till like 10.